Hello there, and welcome to the Sleepy Space Channel. Tonight, we are drifting outward past the edges of our own galaxy and into the long, unhurried quiet between things. The light you will hear about tonight has been traveling for hundreds of millions, sometimes billions of years, and it is still arriving, softly, even now. We will wander through the near shore of the local group, past Andromeda and the gentle glow of the Magellanic Clouds, and further still into clusters and superclusters and the wide, patient architecture of the cosmic web. And at the very end of the drift, we will reach the faintest things the universe has carried this far reddened, ancient, barely there, and entirely real. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Allow the day to fade, quietly, behind you. Let's begin. There is a particular quality to the sky on a clear night, when you are somewhere the lights have gone dim and the air has settled. It doesn't announce itself. It just becomes visible gradually, the way your eyes adjust to a darkened room without any effort on your part. One star, and then several, and then a wash of faint light spreading across the whole overhead curve. It has always been there, of course. You simply needed the quiet in order to receive it. The sky you are looking at on such a night is not simple. It looks uniform, a smooth, dark field scattered with bright points. But it is actually layered in time in a way that has nothing to do with distance as we usually understand it. Distance, for the universe, is not the same as distance across a room, or a field, or an ocean. When you look outward into space, you are not simply looking toward farther and farther places. You are looking backward and backward into time. Every source of light you see has been traveling toward you. Some of those journeys were short. Some were almost incomprehensibly long. And none of them are instantaneous. The light arriving at your eyes right now left its source some time ago. For the nearest stars, that delay is a matter of years, a handful, or a dozen, or a few hundred, depending on which point of light you happen to be watching. For the most distant objects visible to the naked eye, that delay stretches to millions of years. The universe you are observing is not the universe as it is. It is the universe as it was, assembled into a kind of slow archive by the constant speed of light moving across space. When you understand this not urgently, not with alarm, but simply as a quiet fact about the nature of seeing the night sky, becomes something quite different. It becomes a record rather than a window. A soft and patient document of light still arriving. You don't need to hold that idea tightly. It is enough to let it settle in, the way warmth settles into a room from a fire not quite in view. You can feel it without examining every corner of it. The system we live inside, the Milky Way, is itself so large that light takes roughly 100,000 years to cross it from one edge to the other. Most of the stars visible on a clear night are within a few thousand light years of us, which means they are, in cosmic terms, nearby. They are neighbors. Their light is almost fresh compared to what reaches us from farther out. But even the Milky Way, for all its scale, is only one of somewhere between 100 billion and 2 trillion galaxies estimated to exist within what we can observe. It is a home island in a long, quiet ocean. The idea of that ocean is what tonight is about. Not in any urgent or exhausting way, there are no tests to pass, no information you must absorb before something is revealed. The drift is slow, and the direction is soft, and the destination if there is one, is simply a kind of settled familiarity with how large and how old and how gentle the universe actually is when you let it arrive at its own speed. There is something comforting in the fact that the universe does not need anything from you. The galaxies you will hear about tonight are not waiting for your attention. They have been turning slowly for billions of years, and they will continue turning long after any particular observation ends. Light from those galaxies was already on its way toward this corner of the cosmos before the Earth existed, before the solar system had formed, before the atoms that make up your body had even been assembled inside older stars. And now that light arrives, faint and stretched and patient, and we happen to be here to receive it. That is not a small thing, but it is a quiet one. The Milky Way itself, seen from outside if you could be placed far enough away to take it in whole, would look something like a flattened spiral. A disk with arms of stars curling outward from a dense central region, rotating slowly, taking several 100 million years to complete a single turn. It is not a simple object. It is full of gas and old light and dark matter and the slow drift of hundreds of billions of individual stars in their long orbits around the center. And at that center, quiet right now, sits a supermassive black hole, an object around 4 million times the mass of the Sun, pulling the central stars into tight, fast orbits without giving much away. But the Milky Way, for all that, is the shore you are leaving tonight. The water ahead is wider. As the sky settles over you and the last of the day's urgency softens, the outward drift begins. Not quickly. There is no rush. Each part of this journey moves at the pace of light, moving through open space, steady, quiet, and entirely sure of itself. The first thing to arrive when you look outward from the Milky Way is not emptiness. It is company. Light moves at a fixed speed through the emptiness of space, and that speed, while enormous by any everyday measure, is still a speed. It covers approximately 299,792 kilometers every second. In a single year, light crosses about 9.5 trillion kilometers. That distance is what astronomers call a light year, and it is the basic unit of this kind of geography. Not a unit of time alone, and not a unit of distance alone, but in a sense both at once, because a light year of distance means a year of delay. When you look at a star 100 light years away, you are seeing it as it was 100 years ago. When you look at a galaxy 2 million light years away, you are seeing it as it was 2 million years ago. That is not a figure of speech. It is a physical fact rooted in the finite speed of light. There is no shortcut available. Light cannot go faster. Space cannot be told to hurry. The signal arrives when it arrives, and when it does, it brings with it a picture of the source as it existed at the moment the light departed. This means that every act of looking outward into space is also an act of looking backward into time. The two things are inseparable. You cannot look at a distant galaxy without also looking at an earlier version of the universe. This is not a problem to be solved. It is a feature of the cosmos, built into its structure by the fact that space is large and light is finite. Astronomers work with this constantly, and after a while it stops feeling strange. It becomes simply the way things are. The deeper you look, the younger the universe appears. Objects at the very edge of what can be observed are being seen as they existed when the universe was only a few 100 million years old, a small fraction of its current age of around 13.8 billion years. In that early period, things were quite different. Galaxies were smaller, more irregular in shape, forming stars at enormous rates from dense clouds of gas that had not yet been depleted. The smooth, grand spiral forms we associate with mature galaxies had not yet had time to settle into place. Everything was younger and more turbulent, not in a dramatic way, but the way early morning is different from midday, the same place, but at a different moment in its unfolding. As light travels through the expanding universe, something happens to it. Space itself is stretching not into anything, but in all directions simultaneously, and as light moves through that stretching space, its wavelength stretches too. This is called redshift. A beam of light that began its journey at a particular color, blue, say, or green, will arrive at our instruments shifted toward the red end of the spectrum. The longer it has been traveling, the more it has been stretched. The more it has been stretched, the more redshifted it appears. For the most distant objects in the universe, the light has been stretched so dramatically that it has moved entirely out of the visible range and into infrared wavelengths. Light that is invisible to the eye, but detectable by the right instruments. This is one reason why the James Webb Space Telescope was designed to observe primarily in infrared. The ancient light from the earliest galaxies is no longer arriving as visible light at all. It arrives as long, stretched, reddened signals that have been traveling since the universe was very young. Infrared detectors collect those signals the way a very patient ear might collect sound from a great distance, waiting, gathering, slowly building a picture from what arrives. The idea of infrared as the resting place of ancient light has something almost tender about it. The most energetic, burning, youthful light from the universe's earliest hours has over billions of years of travel settled into the quietest, longest wavelength form. It arrives gently now. It does not announce its great age. It simply reaches the detector after its long journey and contributes to the image of something that no longer exists in the form it once had. Looking at a redshifted galaxy, then, is looking at something that has continued to change over all those billions of years into something we cannot directly see from here. The galaxy we observe existed as we see it when the light departed. What it has become in the intervening time, whether it has merged with a neighbor, stopped forming stars, grown quiet, or changed its shape entirely, we cannot say from that image alone. We are seeing a moment preserved in traveling light, not a live feed. This is the nature of cosmic observation, and there is something surprisingly restful about accepting it. Consider the sky above you as a kind of layered archive, not a flat image. At the nearest edge of that archive are the stars of the Milky Way, their light only years or at most thousands of years old. A little farther out, the nearby galaxies of the local group, their light 1 million years old, or 2 million, or a few million at the outer edges. Farther still, the rich clusters of the Virgo region, light perhaps 50 or 60 million years in transit. And, deeper still, light that has been traveling for hundreds of millions, then billions of years, arriving now as faint red smudges in the most sensitive instruments ever built. All of these signals are arriving simultaneously. Right now, in this moment, ancient light is hitting every detector and open eye on Earth. The archive is being consulted in real time, from many different depths at once. And there is no hierarchy among these signals. The ancient light from a distant galaxy is not more important than the nearby light from a neighboring star. They are all simply arrivals. They all made the journey and arrived. Something you might find quietly interesting is this. There is no such thing, in astronomy, as a present tense observation. Every measurement is historical, by definition. Even the nearest star beyond our Sun, Proxima Centauri, at about 4.2 light-years away, is seen as it was roughly 4 years ago. Even the Sun itself, which you might think of as very immediate, is seen as it was 8 minutes and 20 seconds before the light from it reached your eye. The Sun you see in your mind, when you imagine a clear afternoon, is already a story about the past, told in photons that left the surface 8 minutes ago and spent that time crossing the emptiness of the solar system. When you extend this principle outward to galaxies, the delays become vast enough that ordinary intuitions stop working. A galaxy 2 billion light-years away is seen as it was 2 billion years ago, long before any of the complex chemistry of life on Earth had developed, long before the solar system existed, long before the gas that would eventually form the solar system had been expelled from dying stars and gathered into anything. The galaxy you are looking at was already old when the story of this small, unlikely planet had barely begun. And yet, the light continued. Through 2 billion years of expanding space, through the slow stretching of wavelengths, through the long, patient crossing of all that distance, the signal kept going. There was nothing to stop it. Space does not absorb light the way air absorbs sound. It simply crosses. And so it crossed, and crossed, and crossed, until it arrived here where it would not be received for billions more years, and now it is received, and the moment of its departure is visible in a way it could not have been predicted to be visible when it left. There is something quite beautiful about that. Not beautiful in an exclamatory way. Just quietly beautiful, the way a piece of information can be beautiful when it is true and strange and asks nothing of you. The galaxies at the most extreme distances visible to current instruments existed when the universe was only a small fraction of its current age. Some of them are irregular, bright, compact, full of young stars burning hot and fast. They look nothing like the orderly spirals and ellipticals we see in the nearby universe because they had not yet had time to become those things. The universe was still early in its own development, still settling, still forming the large-scale structures that would eventually define its shape. Those early galaxies were part of that settling condensations of matter in a young and cooling universe, beginning the long work of star formation that would, over billions of years, produce the galaxies we can see today in their more mature forms. This is one of the most remarkable things about the observatory we are all inside. The sky contains all ages of the universe at once. You do not need to travel in time to see the past. The past is visible from where you are, at every moment, in every direction. The sky is not a background. It is a record. And it is a long, patient, extraordinarily detailed record of a universe that has been quietly doing its work for almost 14 billion years. As you settle into the idea of light as a traveling messenger, not instantaneous, not urgent, but steady and constant, the nearby galaxies begin to feel different. They are not abstractions at a safe intellectual distance. They are places. They are places from which light has been arriving for a very long time, long before any being was present to receive it, long before this planet existed to stand on. And now you are here, and the light is arriving, and the quiet fact of that is as close to ordinary as anything else that happens in a night sky. The nearest of those places, the galaxies that share the local group with the Milky Way, are where the drift continues next. They are, in cosmic terms, our neighbors. Not close enough to visit, and not close enough to see in much detail with the naked eye, but close enough that their light arrives with something that almost resembles familiarity. The Milky Way does not travel alone. It belongs to a small family of galaxies that are gravitationally bound to one another. Bound meaning that their mutual attraction is strong enough to keep them moving together, rather than drifting apart on the general current of Cosmic expansion. This family is called the local group. It contains somewhere around 80 galaxies, though most of them are small, dim dwarf galaxies that barely register at any meaningful distance. The two dominant members are the Milky Way and the Andromeda Galaxy. Between them and around them, a quieter collection of smaller companions, orbits, and drifts. The local group occupies a region of space that spans roughly 10 million light-years across. That sounds enormous, and it is enormous, but within the broader context of the universe's structure, it is a small, self-contained neighborhood. Its members are not drifting apart from one another in the way that distant galaxies are receding. The expansion of space operates on the very largest scales, but within a gravitationally bound system like the local group, the members hold together. They move relative to one another, sometimes slowly approaching, sometimes orbiting, but they are not carried away on the expansion the way unbound galaxies are. Andromeda is the nearest large galaxy to the Milky Way. Its light takes approximately 2.5 million years to cross the space between us. 2.5 million years. When that light left Andromeda, early hominids were just beginning to appear on Earth. The landscape of this planet was entirely different. The animals were different, the continents were subtly different, the climate was different. And yet the light from Andromeda was already on its way, and it has been traveling ever since. And when you look at a dark sky and find that faint smear in the constellation Andromeda just barely visible to a careful naked eye, under good conditions, you are receiving light that departed 2.5 million years ago, from a place containing somewhere around 1 trillion stars. Andromeda is somewhat larger than the Milky Way. It is a spiral galaxy, like ours, with a broad disk of stars and gas and a bright central region. It appears to our instruments as a long, slightly tilted oval, because we are seeing it at an angle not from above or below, but from the side or close to it. If we could see it face on, it might look something like a textbook spiral, with arms curling outward from a bright core. From our angle, the shape is more compressed, more elongated, more like an ellipse of light with a brighter center. Andromeda is moving toward the Milky Way. The two galaxies are approaching each other at roughly 110 kilometers per second. This sounds fast. In ordinary terms, it is fast, faster than almost anything in everyday experience. But the distance between them is so enormous that even at that speed, the merger will not begin for somewhere around 4 to 5 billion years. And the merger itself, when the two galaxies eventually grow close enough to significantly distort one another, will take another several billion years to fully play out. It is not a collision in any sudden sense. It is a gravitational encounter measured in geological time, in deep time, in the kind of time that makes the history of this planet seem brief. When the two galaxies eventually interact, the result will not be the destruction of their stars. Stars are so far apart within any galaxy that almost none of them will physically collide, even during a full galactic merger. What changes is their orbits. The gravitational interaction will fling stars into new paths, redistributing them over a broader region of space. The neat disk structures of both galaxies will be disturbed and eventually reshaped into something different, probably a large elliptical galaxy, rounder and more diffuse than either of the original spirals, with stars spread out in more elongated orbits rather than the flat rotating disk that currently defines the Milky Way. But this is not something to think about with any urgency tonight. It is simply part of the long, slow story of how galaxies evolve. Every large galaxy in the universe has experienced mergers. The Andromeda Galaxy itself bears the evidence of earlier encounters with smaller galaxies, a faint stream of stars stretching away from its main body, the leftover trail of a smaller companion that was gradually absorbed. These streams are quiet archives. They mark where something passed through and was slowly incorporated. The Triangulum Galaxy is the third largest member of the local group. It sits a little over 2.5 million light-years away, a distance similar to Andromeda, and it is a spiral galaxy, somewhat smaller and less dramatic than either the Milky Way or Andromeda. Its spiral arms are looser, more open, giving it a softer, more relaxed appearance than the tightly wound spirals of some other galaxies. It is one of the most distant objects visible to the naked eye under very dark skies, appearing as an extremely faint, diffuse smear, barely there. Easy to miss, but present for those patient enough to look. The Triangulum Galaxy is notable for its ongoing star formation. It contains a very large population of star-forming regions, areas of dense gas where gravity is drawing material together into new stars. These regions glow in particular wavelengths of light, producing the pinkish haze that shows up in long-exposure photographs. Triangulum is, by the standard of nearby galaxies, quite active busy in the quiet astronomical sense of that word, where busy means producing new stars at a notable rate, rather than having settled into the quieter phase of an older galaxy that has used up most of its available gas. Closer in, arranged around the Milky Way like two small attendants, are the Magellanic Clouds. These are not visible from most of the northern hemisphere, but from the southern latitudes they are simply there in the night sky, visible to the naked eye as two detached fragments of the Milky Way, a larger and a smaller patch of soft light, hanging in the sky separately from the main band of the galaxy. The large Magellanic Cloud sits about 160,000 light-years away. The small Magellanic Cloud is slightly farther, around 200,000 light-years. By the standards of the local group, these are very close. Their light is only 160,000 or 200,000 years old when it arrives. In cosmic terms, that is almost immediate. And yet even that nearness contains something humbling. 160,000 years ago, on Earth, there were no cities, no written language, no agriculture. Human beings existed, but our entire recorded history had not yet begun. The light from the large Magellanic Cloud that you might see tonight left that galaxy at a time when the entire human story, as we know it, had not yet started. The Magellanic Clouds are irregular galaxies. They do not have the clean disk structure of a spiral. Their shapes are ragged and asymmetric, partly because of their own relatively small size and partly because of their interactions with the Milky Way. The Milky Way's gravity has been pulling at these galaxies for a very long time, stretching tidal streams of gas away from them in a long arc that wraps around part of the sky. This stream of hydrogen gas, called the Magellanic Stream, is an enormous ribbon of material extending across a significant portion of the southern sky, a physical record of the gravitational interaction between three galaxies over hundreds of millions of years. The interaction also triggers star formation in the Magellanic Clouds. The tidal forces from the Milky Way compress gas in certain regions, causing it to collapse into new stars. The large Magellanic Cloud contains a star-forming region called the Tarantula Nebula that is one of the most active in the entire local group. A vast complex of gas and young stars generating so much radiation that if it were placed at the same distance as the Orion Nebula, it would cast faint shadows on Earth at night. But from 160,000 light-years away, it appears as a small, soft feature in a hazy patch of light. All of these galaxies, Andromeda, Triangulum, the Magellanic Clouds, the dozens of smaller dwarf companions scattered through the local group, are moving. They are orbiting, drifting, slowly interacting over timescales that dwarf the history of any civilization. None of this motion is perceptible in a human lifetime. The sky looks exactly the same to you tonight as it looked to every human who ever looked up at it from this planet. The changes happen on scales of millions of years, and a million years is a span that human intuition simply cannot contain. This is, in its own way, a comfort. The sky is stable for your entire lifetime. The galaxies are where you expect them. The light arrives on the same schedule it always has. And below the apparent stillness, an enormous gravitational dance proceeds at its own patient pace, indifferent to urgency, moving according to rules that operate on the slowest possible timescales. The local group as a whole is itself moving. It is falling, along with many other galaxy groups, toward a region of greater mass concentration toward the richer, denser parts of the larger cosmic structure. But that is a story for a little later in the night, when the drift has expanded outward past the familiar neighborhood and into wider waters. For now, just the local group, and its slow turning, and its millions of years-old light arriving here in the dark. Galaxies are not all the same shape, and that simple fact turns out to be one of the most quietly revealing clues about how the universe works on long timescales. At first glance, galaxy shapes look like classification, a way of sorting distant objects into categories for convenience. Spirals, ellipticals, irregulars, lenticulars. Clean labels. But when you stay with it longer, something shifts. These shapes stop feeling like types and start feeling like outcomes. Each one is the visible result of an extremely long history, written slowly in stars and gas across hundreds of thousands of light years. A galaxy is not frozen. It is not a completed object. It is a process that happens to be stable enough, for long enough, that we can catch it mid-story. The shape we see is not accidental decoration. It is a physical record of everything that has happened to that system. How much gas it once had, how it formed its first stars, whether it collided with neighbors, whether it lived in isolation or in a crowded cluster, and whether it has been quietly evolving or repeatedly disturbed by gravitational encounters. If you could read a galaxy's shape the way you read lines in a book, you would not just see what it looks like, you would see what it has lived through. Spiral galaxies are the most familiar in this visual language, partly because they are so striking, and partly because we live inside one. From the outside, a spiral galaxy looks like a broad disk of light with a bright central region and sweeping arms that curve outward in elegant arcs. The Milky Way belongs to this class, as do Andromeda and Triangulum. From a face-on perspective, a spiral galaxy can look almost symbolic, like a diagram of motion made visible, a luminous center surrounded by a rotating pattern of structure that seems to extend outward into space. But that elegance hides something more subtle. Spiral arms are not solid structures. They are not rigid formations made of the same stars bound together like a physical object. That is the intuition many people start with, but it is slightly misleading. The arms are better understood as regions of density enhancement areas, where stars, gas, and dust become slightly more concentrated as they orbit the galactic center. The term astronomers use is a density wave, and it describes a phenomenon that is far more dynamic than the visual impression of graceful, static curves would suggest. A useful way to imagine this is to think of a slow-moving traffic jam on a circular highway. Cars are not permanently part of the jam. They enter it, slow down as congestion increases, then eventually exit and continue on their way. The jam itself persists, even though its individual contents are constantly changing. Spiral arms behave in a similar way. Stars and gas move through them, not with them. The pattern remains, even though the material composing it is always shifting. This distinction matters enormously for understanding what spiral galaxies actually are. Not fixed wheels of star stuff, but persistent waves of gravitational pressure rolling through a sea of orbiting matter. This means that the Sun is not fixed inside any particular spiral arm of the Milky Way. Over its long orbit around the galactic center, it has likely moved in and out of different arms multiple times. Each passage is slow on human timescales, but over hundreds of millions of years, the solar system has experienced different regions of density, different star-forming environments, and different gravitational conditions, all without ever leaving the galaxy. Whether this has influenced Earth's geological or biological history is an open and genuinely fascinating question, though establishing direct causal links across such vast timescales remains difficult. Where spiral arms contain enough cold gas, they become sites of active star formation. Gas clouds within these regions can become compressed by the density wave passing through them. When this happens, gravity takes over. The cloud begins to collapse inward, becoming denser and hotter. Pressure builds from the inside as the cloud fights against its own gravitational contraction. But under the right conditions, sufficient mass, low enough temperature, and enough time, gravity wins. Eventually, conditions become extreme enough for nuclear fusion to ignite in the core of the collapsing region, giving birth to new stars. These newly formed stars are not like the long-lived, relatively stable stars that dominate a galaxy's older population. They tend to be massive, extremely hot, and very luminous. Because of their high temperatures, they emit light that is strongly shifted toward the blue end of the spectrum. This is why spiral arms often appear brighter and bluer than the surrounding disk they are populated, at least in part, by these young stellar regions. The color of a galaxy, it turns out, is not cosmetic. It is diagnostic. Blue regions indicate recent star formation. Redder regions indicate older stellar populations where active star formation has slowed or ceased entirely. But these massive young stars live fast and die young. A star many times the mass of the Sun can exhaust its nuclear fuel in a fraction of the time that a smaller, dimmer star would take. In cosmic terms, they are brief flashes of intense brightness. When they end their lives, often in violent supernova explosions, they do not simply disappear. They return enormous amounts of material to the surrounding medium, enriching it with heavier elements forged in their cores: carbon, oxygen, iron, and everything beyond. This material then becomes part of future generations of stars, continuing the cycle of formation and evolution. In this sense, spiral arms are not just beautiful features of a galaxy's face. They are the sites where the universe builds complexity. Not all galaxies follow this spiral pattern. Many of the most massive systems in the universe belong to a different category entirely: elliptical galaxies. These objects do not have disks, arms, or obvious internal structure. Instead, they appear as smooth, rounded, or slightly elongated distributions of light. The brightness is highest in the center and gradually fades outward without sharp transitions or features. Where a spiral galaxy has a certain energy to it, a sense of motion encoded in its form, an elliptical galaxy projects something closer to stillness. Elliptical galaxies are dominated by older stellar populations. Their stars are generally cooler and redder than those in spiral arms. This color shift reflects a long history in which star formation has largely slowed or stopped. The primary reason for this is the lack of cold gas. Without gas to collapse into new stars, the galaxy cannot easily replenish its stellar population. What remains is a long-lived collection of stars that orbit within a shared gravitational field, gradually aging together like embers slowly cooling after a fire has burned down. These galaxies are often found in dense environments, especially in the centers of galaxy clusters. In such regions, repeated gravitational interactions and mergers play a major role in shaping their evolution. When galaxies fall toward the center of a cluster, drawn in by the enormous collective gravity of hundreds or thousands of other galaxies, they can be absorbed by larger systems. Gas is stripped away by the hot intracluster medium, the diffuse, superheated plasma that fills the space between galaxies in a cluster. Without that gas, the raw material for star formation simply disappears. The galaxy is starved of the fuel it would need to maintain or renew itself, and it gradually transitions into a quieter, redder state. The growth of elliptical galaxies through mergers is not sudden. It is not a dramatic collision in the everyday sense. Instead, it is a slow gravitational transformation that can unfold over billions of years. As a smaller galaxy approaches a larger one, tidal forces begin to stretch and distort it. Its outer regions are stripped away first, since those stars are held less tightly by their galaxy's gravity. Gradually, the smaller system is pulled apart, and its stars are redistributed into the larger galaxy's extended halo, a diffuse outer region that can contain enormous numbers of stars in relatively loose orbits. Over millions or billions of years, the original structure of the smaller galaxy disappears entirely, leaving behind only a subtle contribution to the larger system's stellar inventory. The result of many such mergers, accumulated over cosmic time, is often a giant elliptical galaxy, a vast diffuse structure containing enormous numbers of stars spread over a large volume of space. Some of these systems contain trillions of stars, far exceeding the stellar population of typical spiral galaxies. Despite their immense scale, they appear relatively calm. They do not show obvious signs of active star formation. They lack the patchwork blue regions and dusty lanes that give spirals their texture. Instead, they represent the quiet accumulation of long histories, galaxies that have lived through many encounters and settled, finally, into a kind of equilibrium. Between spirals and ellipticals lies another class that resists easy characterization: lenticular galaxies. These objects share features of both types. They have a disc-like structure similar to spirals, but lack the prominent arms and active star-forming regions that make spirals so visually distinctive. They often appear smooth and featureless in their discs, like spirals that have lost their defining texture. Without the arms, without the blue star-forming knots scattered through the disk, a lenticular galaxy looks like a spiral that has been gently erased. One common explanation for lenticular galaxies is that they are spirals that have lost their gas. This can happen in dense environments, such as galaxy clusters, where interactions with the hot intracluster gas can exert a kind of pressure that sweeps cold gas out of an infalling galaxy, a process called ram pressure stripping. Gravitational encounters with neighboring galaxies can have a similar effect, disturbing the gas distribution until it is no longer able to form stars efficiently. Without cold gas, the spiral arms lose the raw material that defines them. They fade. The disk persists, because the stars that were already there continue to orbit, but the arms, those bright, blue, gas-rich features, gradually dissolve into the general background of the disk. Lenticular galaxies are particularly interesting because they suggest a possible evolutionary pathway. A spiral galaxy is not necessarily a permanent structure. Under the right environmental conditions, it may transition into a lenticular form over billions of years, changing its appearance without a catastrophic merger or collision. The change is gradual, driven by environment, and the slow depletion of resources rather than sudden disruption. This makes lenticulars something like a transitional state, not a final form, but a stage in a longer story. Irregular galaxies occupy yet another part of this spectrum. These systems do not fit neatly into spiral or elliptical categories. They lack symmetry, consistent structure, or clearly defined features. Instead, they appear chaotic or uneven, often as a result of gravitational interactions, mergers in progress, or the conditions that prevailed during their early formation. Some irregular galaxies are small and gas-rich, actively forming stars in localized but intense regions. The chaotic appearance is partly a reflection of the patchiness of that star formation. Bright knots here and there, dark dust lanes cutting through them, no obvious center organizing the whole. Others are being distorted by nearby larger galaxies, their shapes stretched into unusual forms by tidal forces that pull more strongly on one side than the other. The Magellanic Clouds, the two irregular dwarf galaxies that orbit the Milky Way, are nearby examples of this kind of distortion. They are slowly being shaped by the Milky Way's enormous gravitational influence, and streams of gas have already been pulled out of them and stretched across the sky in a structure known as the Magellanic Stream. Over cosmological time, they may be further distorted, tidally shredded, or eventually absorbed entirely into the larger galaxy they orbit. It would be a mistake, though, to think of irregular galaxies as failures or deficient systems. They are simply galaxies in different conditions or stages of evolution systems that have not yet settled into a stable configuration, or that have been knocked out of one. In the early universe, when galaxies were still forming and the rate of gravitational interactions was much higher, irregular shapes were likely far more common than they are today. The relative scarcity of irregular galaxies in the modern universe may itself be evidence of how much settling and merging has occurred over the past 13 billion years. Galaxy mergers are one of the most important processes driving changes in shape over cosmic time. When two galaxies interact gravitationally, the outcome depends on many factors: their relative masses, their velocities, the angle at which they approach each other, and their internal composition, particularly how much gas they contain. But in general terms, mergers between similar-sized spiral galaxies tend to produce elliptical galaxies. This represents one of the primary channels through which the elegant, structured spirals of the earlier universe are gradually converted into the smooth, featureless ellipticals that dominate the centers of today's galaxy clusters. During a merger, the orderly rotation of each galaxy is disrupted. Stars are thrown into new orbits by the changing gravitational field, and the original disk structures are gradually destroyed as order gives way to chaos. Gas clouds from both galaxies can collide and compress, sometimes triggering dramatic bursts of star formation, a starbursting phase that can briefly make the merging system one of the most luminous objects in its part of the universe. But this phase is usually temporary. Eventually, as the system settles and the gas is consumed or dispersed, the result is a more spheroidal distribution of stars, rotating not in an ordered disk, but in a complex tangle of orbits distributed in 3 dimensions, an elliptical galaxy. One of the closest and most visually striking examples of a galaxy transformed by past merger activity is Centaurus A. Located about 13 million light-years away, it appears as a large elliptical structure with a conspicuous dark band of dust cutting across its center. That dust lane is the remnant of a smaller spiral galaxy that was absorbed in the relatively recent past on astronomical timescales. The material from that spiral has not yet fully mixed into the larger system, leaving behind a visible and dramatic trace of the collision. It is a scar, in a sense a sign that the smooth elliptical structure we see today was not always so quiet. At its center, Centaurus A also hosts a supermassive black hole that is actively drawing in material and launching powerful jets of energy into the surrounding environment. Even without that extraordinary activity, however, the galaxy itself already tells a compelling story: collision, assimilation, and long-term transformation. It is a snapshot of a system that has changed dramatically over time and is still, by some measures, in the process of settling. Another well-known spiral system offers a different kind of lesson. The Whirlpool Galaxy presents one of the clearest examples of a grand design spiral structure. A system where the arms are unusually well-defined and symmetrically arranged around a bright, compact central region. The clarity of its arms is not accidental. A smaller companion galaxy lies nearby, and their gravitational interaction plays a direct role in shaping and maintaining the spiral pattern. The companion's gravitational influence helps sustain the density waves that define the arms, preventing them from becoming too diffuse and maintaining the regularity that makes the whirlpool such a visually compelling object. A faint bridge of material stars and gas drawn out by gravitational forces connects the two galaxies, a subtle but real structure that records the history of their interaction. Over time, this interaction will continue to evolve. The companion will draw closer, the bridge will broaden, and the shapes of both systems will gradually change. The whirlpool, as it appears today, is a temporary configuration, and its future form will be written by the continuing gravitational conversation between the two galaxies. When all these types are considered together, a deeper picture emerges. Galaxy morphology is not a fixed taxonomy, but a dynamic spectrum. Spirals, ellipticals, lenticulars, and irregulars are not isolated categories, but stages and outcomes shaped by environment and time. A spiral today may become an elliptical in the distant future. An irregular system may settle into a more stable form over billions of years, or it may be absorbed entirely by a larger neighbor. Even large ellipticals continue to grow slowly through mergers and the steady accretion of smaller companions. The Milky Way itself is not exempt from this story. It is currently on a slow collision course with the Andromeda Galaxy, and in roughly 4 to 5 billion years, the two systems will begin to merge. The process will unfold over an enormous span of time, and its outcome will likely be a large elliptical galaxy, sometimes informally called Milkomeda, that bears little resemblance to either of the two graceful spirals that exist today. The spiral arms, the orderly disk, the familiar shape of our home galaxy, all of this is temporary. It exists now, at this particular moment in the universe's history, because conditions have allowed it to persist. But conditions change, and on long enough timescales, everything transforms. Nothing about a galaxy's shape is permanent. Everything is in motion, but on timescales so vast that the changes are invisible within a human lifetime. What we observe in any given moment is a snapshot, a single frame extracted from a process that spans billions of years. And because light takes time to travel, even that snapshot is already ancient by the time it reaches us. When we observe a galaxy 100 million light-years away, we are seeing it as it existed 100 million years ago. The light carrying that image left its source before complex life existed on Earth. This temporal dimension adds another layer of meaning to morphology. The shapes of distant galaxies are not just records of their own histories, they are records from different epochs of the universe. A galaxy observed at great distance is seen early in its history. A nearby galaxy is seen as it is today, relatively speaking. Mapping the distribution of shapes across different distances amounts to watching the universe age in slow motion, tracing the gradual evolution of structure from the chaotic irregularity of the early cosmos toward the more settled and varied population of galaxies that exists now. In the end, galaxy shapes are not just classifications. They are records. They are physical memories, written in light and structure, telling stories of formation, interaction, and transformation across cosmic time. The spiral arms sweeping outward from a galaxy's bright core, the smooth and featureless glow of a giant elliptical, the asymmetric sprawl of an irregular court mid-collision, each one is a chapter in a very long story. We are simply reading it from the middle, in a single moment, with instruments that can only capture so much at once. But the story is there, patient and vast, encoded in the shapes of the galaxies themselves. Beyond individual galaxies and small groups, the universe begins to organize itself into structures so large that they subtly change the way scale itself is perceived when it is imagined across deep time and distance. At these extremes, gravity is no longer shaping isolated systems in the familiar sense of solar systems or even individual galaxies. Instead, it becomes a sculpting force, acting across hundreds of millions of light-years, guiding matter into vast, connected regions of density, separated by enormous stretches of relative quiet. The shift in perspective required to comprehend this level of organization is not merely quantitative, it is qualitative. The universe at large scales does not simply look like a bigger version of what exists at small scales. It looks like something else entirely. Galaxies are not scattered randomly through this cosmic expanse. They are gently drawn toward regions where matter has already begun to accumulate, following the contours of a gravitational landscape that was shaped in the universe's earliest moments and has been evolving ever since. Over time, they trace out invisible pathways, as though following currents in an ocean too large to see in a single view. They gather where gravity has already deepened that landscape. They cluster where those pathways intersect, forming dense nodes of structure. And between those nodes lie immense regions where galaxies are comparatively rare, sometimes separated by distances so large that light itself takes hundreds of millions of years to cross from one region to another. These quiet expanses are not simply gaps between structures. They are structures in their own right, defined by absence, shaped by the same forces that built everything around them. This arrangement is known as the large-scale structure of the universe, and it carries a geometry that feels at once ordered and organic. When it is mapped in 3 dimensions, a striking pattern emerges. Rather than a uniform spread of matter, the universe reveals itself as a vast network of filaments stretching across space, punctuated by dense clusters and surrounded by broad, quiet voids. Some descriptions compare this to foam, where thin walls separate large, empty bubbles. Others describe it as sponge-like, full of interconnected cavities. But the most enduring image is that of a web, a cosmic web, where matter traces long strands across a background of near vacancy, connecting distant nodes into a coherent, evolving structure. This web is not the result of any local process. It is the evolved consequence of conditions that existed in the very early universe, when matter was almost but not quite perfectly uniform. Tiny irregularities in the density of matter, fluctuations so small that they seem negligible, were slowly amplified by gravity over billions of years. Regions that were marginally denser attracted slightly more matter. That additional matter deepened the gravitational well further, drawing in still more. The cycle compounded, slowly but inexorably, over cosmic time. Meanwhile, Regions that were marginally less dense were gradually drained of their matter, becoming increasingly sparse as their contents migrated toward denser surroundings. What began as almost imperceptible unevenness eventually became the dramatic contrast between the filaments and voids we observe today. The cosmic web is, in this sense, the universe's memory of its own earliest moments, inscribed in the arrangement of matter across billions of light-years. The nearest major structure of this kind to our own local group of galaxies is the Virgo cluster. It lies roughly 55 million light-years away and represents one of the most significant concentrations of galaxies in our immediate cosmic neighborhood. Within a region spanning several million light-years, it contains on the order of 1,000 to 2,000 individual galaxies. These galaxies are not evenly distributed within the cluster. Instead, they are drawn toward the central regions where gravity is strongest and where the accumulated mass of the cluster has created a deep gravitational well that has been forming over billions of years. The outer regions of the cluster are less densely packed, containing smaller groupings and chains of galaxies that are still in the process of falling inward. Many of the galaxies in this dense environment are elliptical or lenticular in shape. These systems tend to have smooth, rounded appearances, with little visible structure such as spiral arms or active star-forming regions. Their light is dominated by older stellar populations, giving them a softer, more uniform glow. This appearance reflects a long history of internal evolution shaped heavily by their environment. In many cases, these galaxies have already consumed or lost most of their interstellar gas, the raw material needed to form new stars. Without that material, star formation slows dramatically, and the galaxy settles into a quieter state. The dense cluster environment is itself responsible for much of this transformation. Hot intracluster gas exerts a kind of pressure on infalling galaxies, sweeping their cold gas away before it can be converted into stars. Gravitational encounters with neighboring galaxies disturb their internal structure further. The cluster, in a sense, slowly processes the galaxies that fall into it, stripping away the features that distinguish young, active systems and leaving behind the smoother, older remnants that cluster environments are known to harbor. At the center of the Virgo cluster lie several, especially massive, elliptical galaxies. These central systems are among the largest known types of galaxies in the universe, enormous accumulations of stars that have grown through repeated mergers over the entire history of the cluster. They are not isolated objects, but the result of long-term accumulation processes. Over billions of years, smaller galaxies have fallen inward toward the cluster center, pulled by the deepening gravitational well. As they do, tidal forces and gravitational interactions disrupt their structures. Stars are stripped from their original orbits and gradually absorbed into the larger system. Thin, diffuse halos of stars extend outward from these central giants, recording the memory of the many smaller galaxies that have been dismantled and assimilated over cosmic time. In their structure, these central ellipticals contain the histories of dozens or hundreds of predecessors. There is also a temporal dimension to our view of the Virgo cluster worth dwelling on. The light we observe today from these galaxies began its journey 55 million years ago. At that time, Earth was in a very different stage of its biological history. The age of non-avian dinosaurs had already ended. Mammals were beginning to diversify into a wide range of forms and ecological roles, spreading across landscapes that no longer exist in their ancient configurations. Early ancestors of future primates were small, adaptable creatures navigating changing environments. None of what has happened in Earth's subsequent history, the rise and fall of entire lineages, the shaping of continents, the emergence of intelligence had yet occurred when the photons we now observe first departed the Virgo cluster. Those photons have been traveling undisturbed through the universe ever since, carrying an image of the cluster as it was in that distant past, arriving here only now. Every observation of the Virgo cluster is therefore not just a view of a place, but a view of a moment 55 million years in the past, preserved in light. The Virgo cluster itself is part of an even larger structure. For much of the 20th century, it was described as the center of the Virgo supercluster, a region of space that included the Milky Way and its local group as outlying members. More refined mapping of the cosmic environment using galaxy motions has revealed something more nuanced and more remarkable. The Milky Way, the Virgo cluster, and a vast surrounding region of space all participate in a broader gravitational flow system called Laniakea. The name, drawn from the Hawaiian language and meaning immeasurable heaven, reflects both the scale of this structure and the difficulty of fully grasping its extent in intuitive terms. Unlike a galaxy cluster, which is gravitationally bound and will remain a coherent system indefinitely into the future, Laniakea is defined not by containment, but by motion. It is a region of space where galaxies, including the Milky Way, are gradually drifting along shared gravitational pathways that converge toward a common directional flow. It is a watershed, in a sense not a body of water, but a body of directed gravitational influence, within which rivers of galaxies flow toward a common basin. At the center of this flow lies a region known as the Great Attractor. It is not a single object that can be clearly isolated or pointed to on a map in the way that a galaxy or cluster can. Instead, it is a broad gravitational influence produced by an uneven distribution of mass across a large portion of space, a concentration that includes the Norma cluster, the Centaurus cluster, and other significant accumulations of matter, all contributing to a combined gravitational pull that influences galaxy motions across hundreds of millions of light-years. Its presence is inferred largely from the way galaxies in the surrounding region appear to be moving not randomly, but converging toward a shared direction, as though drawn by something beyond the visible. Much of the Great Attractor region is obscured by intervening dust and gas in the plane of the Milky Way, making it difficult to observe directly in optical light. X-ray and radio observations have partially penetrated this obscuration, but the full picture remains incomplete. The Milky Way and the local group are part of this flow. Our galaxy is not stationary in space, nor is it isolated from the broader gravitational environment. It is slowly drifting, along with its neighbors, along the gravitational currents of Laniakea. However, the timescales involved are so vast that this motion is entirely imperceptible in any human sense. Even over millions of years, the change in position is only a small fraction of the distances involved. It is motion without sensation, drift without awareness, entirely real, entirely measurable through careful analysis of galaxy velocities, and yet entirely outside any direct experience. Beyond Laniakea, the universe expands into the broader architecture of the cosmic web. When the positions of galaxies are mapped across enormous regions of space, a consistent pattern emerges regardless of which direction is examined. Instead of being evenly distributed, galaxies trace long, thin filaments that stretch across hundreds of millions of light-years. These filaments intersect at nodes where galaxy clusters form, creating dense hubs of gravitational activity where matter has accumulated most intensely. Between these filaments and nodes lie vast voids, regions where the density of galaxies is significantly lower than the cosmic average. The largest known voids span hundreds of millions of light-years. Within such regions, the structure of the cosmic web becomes less visually prominent. Galaxies are more widely separated, clusters more distant, and the overall impression is one of vastly reduced density. The Botez void, discovered in the 1980s, was among the first to attract widespread attention. Its scale was initially so surprising that it prompted genuine debate about whether the standard model of cosmic structure formation could account for it. Subsequent surveys revealed that voids of comparable scale are common features of the cosmic web, consistent with what models of large-scale structure predict when dark matter and ordinary matter interact over billions of years of gravitational evolution. These voids are not truly empty in an absolute sense. They still contain dark matter, diffuse gas, and occasional isolated dwarf galaxies that formed and evolved in relative isolation, far from the gravitational influence of clusters and massive filaments. However, compared to the dense filaments and clusters, they appear comparatively sparse. Their structure is defined not by what is present, but by what is relatively absent. In this way, the voids of the cosmic web carry their own kind of information. They record the degree to which matter has been drawn outward and away from them, redistributed into the denser regions that surround them. A central and indispensable component of this entire architecture is dark matter, an unseen form of mass that does not interact with light in any way we have yet detected. It does not emit radiation, does not absorb it, does not reflect it. It makes no contribution to the light gathered by telescopes. Yet it exerts a strong gravitational influence on everything around it, and its effects are measurable in the motions of galaxies, the bending of light around massive structures, and the overall pattern of large-scale structure across the universe. Dark matter is believed to make up the majority of the universe's total matter content, far exceeding the amount of ordinary atomic matter that forms stars, planets, gas clouds, and living systems. In galaxy clusters, the visible matter galaxies and hot intracluster gas accounts for only a fraction of the total mass inferred from gravitational measurements. The rest is dark matter, distributed in extended halos that surround and permeate the visible structures. On the largest scales, dark matter forms the scaffolding of the cosmic web itself, with ordinary matter tracing the outlines of the invisible framework that dark matter established billions of years ago. The story of how dark matter shaped the cosmic web begins in the early universe, when matter was nearly, but not quite, uniform. The tiny density fluctuations that seeded all later structure were present in both the dark matter and the ordinary matter components, but dark matter began to respond to them earlier. Because dark matter does not interact with radiation the way ordinary matter does, it was free to begin gravitationally clustering before ordinary matter could. It formed the first structure's shallow wells in the gravitational landscape into which ordinary matter later fell. By the time ordinary matter was free to respond fully to gravity, it was already falling into a pre-existing scaffold of dark matter. The cosmic web we observe is therefore not purely the work of ordinary matter and gravity alone. It is the imprint of dark matter's earlier gravitational work, traced by the ordinary matter that followed. Inside galaxy clusters, the environment is radically different from the relative tranquility of isolated regions. Galaxies move through cluster environments with high velocities, often hundreds or even over 1,000 kilometers per second relative to one another. Despite these extreme velocities, direct collisions between individual stars within different galaxies are extraordinarily rare. The distances between stars are simply too vast. But the galaxies themselves do interact, gravitationally disturbing one another's structures, stripping away gas, and occasionally merging over extended timescales. Between the galaxies lies the intracluster medium, a hot, diffuse plasma that fills the interior of the cluster and represents a substantial fraction of its total ordinary matter content. This plasma reaches temperatures of tens of millions of degrees or more, so hot that it emits strongly in the X-ray portion of the electromagnetic spectrum. Observations of galaxy clusters in X-ray light reveal this gas in striking detail, tracing the complex, sometimes turbulent distribution of matter within and around the cluster. The heating of this gas is driven primarily by gravitational processes. As matter falls into the cluster's gravitational well, kinetic energy is converted into thermal energy. The intracluster medium is, in this sense, a record of the gravitational work that has been done over the cluster's history. When galaxy clusters merge collisions that unfold over hundreds of millions of years, the intracluster gas plays a distinctive and revealing role. Individual galaxies within the merging clusters largely pass through one another, their vast internal spaces, ensuring that stellar collisions remain vanishingly rare. But the intracluster gas is a continuous medium, and it cannot pass through itself without interaction. It collides, compresses, and heats, producing shock waves that propagate through the plasma and can be detected in X-ray observations as sharp features in the gas temperature and density. The dark matter components of the merging clusters, by contrast, pass through each other with minimal interaction, their presence revealed indirectly through gravitational lensing of background light. In the aftermath of major cluster mergers, the dark matter and gas components are found to be spatially offset from each other, a pattern that provides some of the most compelling observational evidence that dark matter behaves differently from ordinary matter and exists as a distinct component. On the very largest scales accessible to observation, the universe contains structures that strain intuition to its limit. The observable universe spans approximately 93 billion light-years in diameter, a volume that contains hundreds of billions of galaxies organized into the filaments, nodes, and voids of the cosmic web. Within this vast space, some structures are so large that different parts of them are observed at different stages of cosmic history simply because light from their far side has been traveling longer. Observation at these scales is inseparable from observation across time. And yet, for all its scale and complexity, the large-scale universe possesses a quality that is perhaps its most philosophically striking. It has no center. Wherever in the universe an observer might be located, the cosmic web appears to extend outward in all directions with the same general character. Filaments, clusters, and voids are present in every direction. The same laws of physics operate everywhere. The same processes of gravitational accumulation and expansion have shaped matter into the same large-scale patterns, regardless of location. There is no privileged position, no cosmic hub around which everything is arranged, no special vantage point from which the structure of the universe looks fundamentally different. The Milky Way itself resides in a relatively ordinary region of this vast structure. It is part of a small group of galaxies located along a filament within a larger network of cosmic structures. It is not positioned at the center of any major system, nor does it occupy an extreme void. Instead, it exists in a typical environment within the cosmic web, neither especially dense nor especially empty, but part of the broader continuum of structure that extends in all directions. There is something quietly humbling in this realization. The universe does not organize itself around any central point or preferred location. The large-scale structure is not a backdrop, it is an ongoing process. Matter gathers where conditions allow. It flows along gravitational pathways, following the invisible currents shaped by dark matter and reinforced by the accumulation of ordinary matter over billions of years. It concentrates in clusters and disperses into voids. Structures grow, merge, and slowly evolve, always under the combined influence of gravity, drawing matter inward and the expansion of space itself, pushing regions apart on the largest scales. Nothing about this arrangement is permanent. The cosmic web we observe today is a snapshot of a process that began nearly 14 billion years ago and continues without interruption. Clusters are still growing through the accretion of infalling galaxies. Filaments are still channeling gas toward denser regions. Voids are still expanding, slowly emptied of what little they once contained. In the far future, as cosmic expansion accelerates, the most distant structures will recede beyond the reach of any signal. The observable universe will become more isolated, more confined, more bounded by the horizon that expansion draws around any given point. The cosmic web will not disappear, but our access to it will gradually diminish. Within that vast and continuous framework, every galaxy, every cluster, every faint point of light observed in the deepest surveys is part of a larger pattern still unfolding. What is seen at any moment is only a single frame in a process of cosmic evolution that is steady, gradual, and uninterrupted across the full depth of space and time. To look outward at the large-scale structure of the universe is to look both outward and backward simultaneously, to see distance and history superimposed, matter and time wound together into something that is, in the deepest sense, still becoming. When astronomers first pointed some of the most powerful observing instruments at what appeared to be an empty patch of sky, the expectation was modest. It was a region chosen precisely because it looked quiet, dark, and unremarkable a place, with no obvious bright stars, no nearby galaxies, no obvious structure that would dominate the view. The plan was simple: hold the gaze for an extended time, collect as many faint photons as possible, and see what, if anything, emerged from the depths. What came back from that prolonged observation was something entirely different from emptiness. As the exposure time increased and more light was gathered, the darkness slowly dissolved into structure. First, a few faint points appeared, then dozens, then hundreds. Eventually, the image filled with thousands of tiny, delicate smudges of light. Each one of those smudges was not a star, not a cloud of gas, but an entire galaxy, a vast system containing millions, billions, or even hundreds of billions of stars. The region of sky that had once looked blank was, in reality, densely populated with distant worlds of light, stacked behind one another at different depths of time. The most striking realization was not just that the sky contained galaxies, but that it contained so many of them in every direction, at every distance that could be reached by light. Even a patch of sky so small that it could be covered by the tip of a finger held at arm's length turned out to contain thousands of galaxies when observed with sufficient sensitivity. The universe, on its largest scales, does not thin out into emptiness. It remains richly populated, layer upon layer, until it fades only because light itself eventually runs out of time to reach us. These long-exposure observations came to be known as deep fields, and they represent one of the most profound shifts in how the universe is visually understood. Before them, the night sky was mostly a foreground of stars within our own galaxy, with a few faint smudges representing other galaxies beyond. After them, the sky revealed itself as something fundamentally deeper. What looks like darkness is not absence, but distance. What looks like emptiness is filled with ancient light, arriving slowly across billions of years. Each faint point in a deep field image carries an enormous hidden structure. Even the smallest smudge of light is a full galaxy, a gravitationally bound system of stars, gas, dust, and dark matter. Some of these galaxies are relatively mature systems, while others are young, irregular, and still in the process of forming their internal structure. In the deepest observations, many of these galaxies are so far away that their light has been traveling for more than 13 billion years before reaching a detector. They are not being seen as they are now, but as they were in the very early universe, when everything was still in a more compact, rapidly evolving state. At these extreme distances, the universe begins to look fundamentally different. The galaxies are smaller and more chaotic in appearance than the grand spirals and smooth ellipticals familiar in the nearby cosmos. Their shapes are less settled, their internal structures less defined. Many appear as compact clumps of intense light, where large numbers of young, massive stars are forming in concentrated regions. Others show irregular outlines, as if they are still assembling themselves from smaller pieces. The overall impression is not of emptiness or simplicity, but of rapid activity, a universe still learning how to organize itself into stable forms. To see these objects at all requires light that has been stretched and weakened by the expansion of space itself. As the universe expands, the wavelengths of light traveling through it are stretched along with the fabric of space. This process, known as redshift, shifts visible light toward longer, redder wavelengths. For the most distant galaxies, this shift is so extreme that their light no longer appears in visible wavelengths at all. Instead, it arrives in the infrared portion of the spectrum, invisible to the human eye, but detectable with specialized instruments designed to capture these faint, stretched signals. Because of this, modern deep observations rely heavily on infrared-sensitive telescopes. These instruments are not simply looking farther into space, they are also looking further back in time, tuning themselves to the wavelength range where the earliest light has arrived after billions of years of stretching. Without this capability, much of the early universe would remain hidden, not because it is absent, but because its light has shifted beyond the range of human vision. Among the galaxies revealed in these deep observations are some that challenge earlier expectations about how quickly cosmic structures could form. In several cases, galaxies have been detected that appear surprisingly bright and massive for such early times. Instead of being small and faint, as once expected, some of these early systems already contain significant populations of stars and show signs of rapid, efficient growth. This suggests that the early universe may have been capable of assembling complex structures more quickly than some earlier models predicted. These early galaxies existed at a time when the universe itself was still very young. In some cases, they are observed as they were when the universe was only a few 100 million years old, a small fraction of its current age. To place this in perspective, it means that the light reaching us today began its journey long before the Earth existed, long before the Sun formed, and long before any of the familiar structures of our solar system had taken shape. What we are observing is not a distant version of our present universe, but an entirely different era in its history. In these early epochs, star formation was often far more intense than in many galaxies today. Large reservoirs of hydrogen and helium gas, left over from the early universe, collapsed under gravity into dense regions where stars could form rapidly. Without the heavier elements that later generations of stars would produce, the cooling processes that regulate star formation today were different, and in some cases less efficient in the same way. As a result, star formation in some early galaxies occurred in rapid bursts, producing large numbers of bright, short-lived stars in relatively short cosmic timescales. Over time, these early stars lived out their lives and returned material to their surroundings. Through stellar winds and supernova explosions, they released heavier elements into space, enriching the surrounding gas. This enrichment process gradually changed the composition of the universe. Each generation of stars contributed new elements: carbon, oxygen, iron, silicon, building up the chemical complexity needed for later stars, planets, and ultimately the conditions for life as we understand it. The earliest stars, often referred to in theoretical models as population 3 stars, are thought to have formed from gas that contained almost nothing but hydrogen and helium. These stars have not yet been directly observed, but their existence is strongly supported by the patterns seen in later generations of stars and in the chemical composition of ancient gas clouds. Without heavier elements to help cool collapsing gas clouds, these first stars may have formed in larger and more massive configurations than typical stars today. Some may have burned extremely hot and short-lived, ending their lives in powerful explosions that seeded the universe with the first significant quantities of heavy elements. As these processes continued, the universe gradually became richer in chemical diversity. Each cycle of star formation and stellar death added more complexity to the cosmic environment. By the time galaxies like the Milky Way began to take shape, the raw materials available for star and planet formation had changed significantly. The gas clouds from which later stars formed contained not only hydrogen and helium, but also the heavier elements that make rocky planets and complex chemistry possible. In this sense, everything around us, including the atoms in our bodies, is the result of many earlier generations of stars living, dying, and enriching the universe over billions of years. Looking at the most distant galaxies in deep field images is therefore not only an exercise in observing faraway objects, but also a form of looking back through the stages of cosmic development. Each faint point of light represents a different moment in that long unfolding history. Some show the universe when it was already forming stable structures. Others show it when those structures were still emerging from more chaotic beginnings. Together, they form a layered record of cosmic time, compressed into a single image. The process of capturing these images is itself slow and cumulative. Light from the faintest galaxies arrives not as a strong, immediate signal, but as a steady trickle of photons over long periods of time. No single moment of observation is enough to reveal them. Instead, light must be collected patiently, accumulated bit by bit, until the signal becomes clear enough to distinguish from the background. What emerges is not a sudden revelation, but a gradual unveiling, as if the universe is choosing to disclose itself at its own pace. There is a quiet correspondence between this method and the nature of the objects being observed. The galaxies themselves are not rushing or changing in ways that we can perceive. Their light has already traveled for billions of years before reaching us, and what we see is a frozen moment from long ago. In that sense, observing them is less like watching something happen and more like receiving a long-delayed message that has been in transit since the early universe. Beyond even these deepest observations lies a further boundary, the limit of the observable universe. This is not a physical edge, but a horizon defined by time and the finite speed of light. Beyond this boundary, there are almost certainly more galaxies, more clusters, more cosmic structures extending outward in all directions. But their light has not yet had time to reach us. The expansion of the universe has carried those regions beyond the range of causal contact, at least for now. This boundary does not represent an absence of existence. It represents a limit of visibility. The universe beyond it is not fundamentally different from the universe we can observe. It is simply unobserved. It likely contains the same kinds of structures: galaxies, stars, gas clouds, and vast filaments of matter shaped by gravity over cosmic time. It is continuous with what we can see, even if it is not currently accessible to our instruments or our light. In this way, the deep fields, the distant galaxies, and the faintest smudges of ancient light all point toward the same underlying reality. The universe is not sparse or incomplete. It is densely populated, layered in time, and far more extensive than what immediate perception suggests. What appears as darkness is, on longer inspection, filled with structure. What appears as emptiness is, in fact, distance stretched across time. And what appears as the edge of sight is simply the limit of how long light has been able to travel. In the end, these deep observations offer a quiet kind of perspective. They do not reveal a different universe, but a deeper view of the one already present. Each faint galaxy is a reminder that what we see is always part of a longer story, one that began long before any observer existed and continues far beyond any single moment of observation. Some of the most distant objects in the universe are also among the brightest, and at first glance this feels like it should not be possible. Distance in space usually behaves like distance in everyday life. The farther something is, the dimmer it appears. Light spreads outward as it travels, thinning across larger and larger spheres of space. And on top of that, the expansion of the universe stretches the light itself, lowering its energy as it crosses billions of years. In most cases, this makes extremely distant objects fade into near invisibility. And yet there are certain sources so luminous that they remain visible across these immense spans of space and time. They do not just survive the journey of their light, they dominate it. These objects are known as quasars, and they represent one of the most striking examples of how extreme conditions in the universe can briefly outshine entire galaxies. A quasar is not a separate kind of object so much as a phase in the life of a galaxy, specifically the most energetic phase of its central region. At the heart of almost every large galaxy sits a supermassive black hole, an object with a mass ranging from millions to billions of times that of the Sunday. Most of the time, these black holes are quiet, surrounded by relatively empty space and only occasional streams of gas or isolated stars that drift too close. But under the right conditions, when a large supply of matter becomes available, the black hole begins to actively accrete material. Gas, dust, and sometimes even disrupted stars are drawn inward, forming a swirling structure known as an accretion disk. This disk is where the transformation happens. Material does not fall straight into the black hole. Instead, it orbits it, layer upon layer, gradually losing energy through friction, compression, and powerful magnetic interactions. As the gas spirals inward, it is squeezed and heated to extraordinary temperatures. The inner regions of the disk become so energetic that they glow across the electromagnetic spectrum. Unlike a normal star, which emits most of its light in visible wavelengths, an accretion disk around a feeding supermassive black hole radiates broadly, producing radio waves, infrared radiation, visible light, ultraviolet light, and even high-energy X-rays. The disk becomes not just bright, but physically extreme in every measurable way, a place where matter is pushed close to the limits of what stable atoms can endure. The result of this process is a quasar, the luminous, compact core of a galaxy whose central black hole is actively consuming matter at a high rate. The energy output of this region can be so vast that it outshines every star in the galaxy surrounding it. A single galaxy might contain hundreds of billions of stars, each producing light through nuclear fusion, and yet the combined glow of all of them can be overwhelmed by the radiation pouring out of a region smaller than our solar system. In the most extreme cases, the quasar can be hundreds or even thousands of times brighter than its entire host galaxy. This overwhelming brightness is why quasars were not immediately recognized for what they are. When they were first observed, they appeared as simple points of light, sharp, unresolved sources that looked indistinguishable from stars within our own galaxy. Yet their spectra told a different story. The light coming from them was heavily redshifted, meaning it had been stretched by the expansion of the universe during its long journey. This redshift placed them far beyond the boundaries of the Milky Way, at distances of billions of light-years. The only way such distant objects could be visible at all was if they were emitting enormous amounts of energy. Gradually, the understanding emerged that these star-like points were not stars at all, but the brilliant centers of distant galaxies seen during rare, highly active phases of their evolution. One well-studied quasar lies roughly 2.5 billion light-years away. At that distance, intuition might suggest that it should be extremely faint, almost impossible to detect without the most sensitive instruments. Yet under dark skies and with relatively modest telescopic equipment, it can still be observed as a faint point of light. That faintness is deceptive, because what is being seen is not the object as it is now, but the object as it was when the light first began its journey toward Earth. The photons reaching us left their source billions of years ago, carrying with them a record of a galaxy in a highly active state, long before our planet had settled into its current form. As observations extend deeper into space, quasars appear at even greater distances, some so far away that their light comes from a time when the universe itself was less than 1 billion years old. At these early epochs, galaxies were more compact, more chaotic, and richer in gas. Collisions and mergers between young galaxies were more common, and these interactions helped funnel large amounts of material toward their centers. This provided ideal conditions for supermassive black holes to feed rapidly, triggering luminous quasar phases. The presence of such bright objects so early in cosmic history presents an interesting challenge. It implies that some black holes grew to enormous sizes extremely quickly, reaching billions of solar masses in a fraction of the universe's lifetime. How this rapid growth occurred is still being carefully explored, but it likely involves a combination of abundant gas supply, efficient accretion, and possibly the existence of unusually massive initial seed black holes formed in the early universe. The energy released by a quasar is not confined to light alone. In many cases, the central region also produces narrow, highly focused jets of material that shoot outward from the vicinity of the black hole. These jets are launched along the system's magnetic field lines and can travel at speeds approaching a significant fraction of the speed of light. They extend far beyond the boundaries of the host galaxy, cutting through interstellar and intergalactic space like long, invisible channels of energy. As they travel, the particles within the jets emit radiation, particularly in radio wavelengths, making quasars some of the most powerful radio sources in the sky. These jets do not remain narrow forever. Over time, they interact with surrounding gas and slowly disperse, inflating vast lobes of energetic plasma that can stretch over millions of light-years. These structures are often visible only in radio observations, forming enormous, ghost-like outlines far larger than the galaxy itself. They represent the long reach of a single energetic event at a galaxy's core, influencing not just the immediate surroundings but the environment far beyond the visible stellar disk. Quasars were far more common in the early universe than they are today. This reflects the changing conditions of galaxies over cosmic time. Young galaxies contained more cold gas, which is the raw material needed both for star formation and for feeding central black holes. Frequent interactions between galaxies helped channel this gas inward, fueling active accretion phases. Over time, as galaxies evolved, much of this gas was consumed by star formation or expelled by energetic processes, and the rate of black hole feeding decreased. As a result, most galaxies today are no longer in a quasar state. The central black holes remain, but they are typically quiet, existing in a long-term, stable, or low-activity phase. This is also true for our own galaxy. At the center of the Milky Way sits a supermassive black hole, massive and influential, shaping the orbits of nearby stars and contributing to the structure of the galactic core. Yet it is not currently in a quasar phase. It is not actively consuming large amounts of matter, and it does not produce the intense radiation associated with active galactic nuclei. In the distant past, however, it is likely that it did experience periods of greater activity when conditions allowed more material to fall inward. During those times, the center of our galaxy may have briefly resembled the luminous quasars we observe in distant galaxies today. Now it rests in a quieter state, still present, still massive, but largely dormant. When we observe a quasar in the night sky, what we are really seeing is not a single object in the present moment, but a layered message from deep time. The light began its journey when the galaxy was in a highly active phase, with its central black hole consuming matter at extraordinary rates. It traveled across billions of years of expanding space, gradually stretched and redshifted, passing through regions of the universe that are now completely different from how they were when the light first left its source. By the time it reaches a telescope on Earth, it carries only a faint impression of its origin, a point of light that encodes a history of extreme energy and long, uninterrupted travel. And yet, despite their intensity, quasars are not exceptions to the rules of physics. They do not operate under different laws. They are the result of familiar processes: gravity pulling matter inward, angular momentum shaping motion, friction, and magnetic fields converting motion into heat and radiation. What makes them remarkable is not that they break the structure of the universe, but that they represent what happens when those structures are pushed to their limits. The same physical principles that govern a falling leaf or a burning star also govern a quasar. Only the scale changes. There is something quietly grounding in this continuity. Even across billions of light years, even in regions where space itself has stretched enormously, the same rules apply without exception. Light still travels at a constant speed. Gravity still draws matter together. Energy still spreads outward from hotter regions to cooler ones. A quasar is not a departure from this order, but one of its most dramatic expressions. In the end, the brightness of quasars becomes less a mystery of distance and more a reflection of consistency. They remind us that the universe does not change its language when it becomes extreme. It simply speaks the same language more loudly, more intensely, and across far greater distances. And when that light finally arrives here, after billions of years of travel, it does so quietly, a faint point in the sky, carrying within it the long, steady echo of a galaxy's most energetic moment. The universe is expanding. This is not a new idea. It has been understood for nearly a century, but what it means and how it operates is worth holding gently in mind. The expansion is not the motion of galaxies flying outward from a central explosion into pre-existing space. There is no center and no surrounding emptiness being filled. What is expanding is space itself. The metric of distance between things is increasing, and galaxies, on the very largest scales, are carried along with that expansion, the way points on the surface of an inflating balloon are carried apart from one another by the stretching of the rubber. The balloon analogy is imperfect, as all analogies are, but it captures something true. On the surface of a balloon being inflated, no point is the center of the expansion. Every point moves away from every other point as the surface stretches. From any particular point on that surface, Everything else appears to be receding. There is no special location, no origin, no direction the expansion is coming from. It is simply happening, everywhere, simultaneously, as a property of the surface itself, rather than as a movement across any fixed background. The universe behaves this way, but in 3 dimensions rather than 2. Space itself is the thing that is growing. And because light travels through space at a fixed speed, and because that space is growing, the relationship between distance and travel time for light is not as simple as dividing distance by speed. The universe that light set out across is not the same size as the universe it arrives in. The space expanded while the light was in transit, carrying the destination farther from the origin even as the light was making progress. This is why the observable universe, the region from which light has had time to reach us, has a current radius of about 46 billion light-years, even though the universe itself is only about 13.8 billion years old. The universe grew while the light was traveling. Within gravitationally bound structures, within galaxies, within clusters, within groups like the local group, the expansion is overridden by gravity. Gravity holds these structures together against the expansion's tendency to pull things apart. The atoms in your body are not being pulled apart by cosmic expansion. The Earth is not drifting away from the Sun. The Milky Way is not being stretched into a thinner version of itself. At all of these scales, and up through the scale of galaxy clusters, gravity is more than sufficient to maintain coherence. The expansion operates on the spaces between bound systems, not within them. But between galaxy groups and clusters, at scales larger than the range over which gravity can maintain dominance, the expansion wins. Distant galaxy clusters are receding from us, and the rate of their recession scales with distance. The farther away a galaxy cluster, the faster it appears to be moving away. This relationship follows from the expansion of space itself. If space everywhere is expanding at the same fractional rate, then a region twice as far away will accumulate twice the recession velocity, simply because there is twice as much expanding space between here and there. This is not velocity. In the ordinary sense, the galaxies are not moving through space so much as space is growing between them. The distinction matters for very distant galaxies, whose recession speeds, when calculated this way, can exceed the speed of light. This does not violate the principle that nothing moves faster than light through space, because the recession is a property of space expansion, not motion through space. A galaxy receding at faster than light speed is not breaking any rule. It is simply in a region where so much space lies between it and us that the expansion of all that space accumulates to a rate exceeding the speed of light. The galaxy itself is not moving unusually fast through its local environment. It is its local environment, and all the space between that environment and ours, that is growing. The observable universe is defined by a particular horizon, the distance beyond which no light has had time to reach us, even in the full history of the universe. Objects beyond this horizon are not observable, not because anything blocks the view, but because the light they emit has not had time to cross the distance. For very distant objects, the expansion of space means that the light they emit now is losing ground. It is moving toward us, but the space between is growing faster than the light can cross it. These objects are receding at expansion speeds greater than light, and their current light will never reach us. They exist, presumably, in their own part of the universe, doing what galaxies do, but they are permanently beyond our ability to detect. Their past light, the light they emitted long ago, when the universe was younger and those distances were smaller, did reach us, or is still on its way. But their present and future light is lost to the expansion. The observable universe is therefore a sphere, not a physical boundary, but a temporal one. It is the region from which light could in principle have reached us since the universe began. And this sphere is not static. It changes over time. As the universe ages, light from slightly more distant regions has slightly more time to make the journey. In that sense, the observable universe grows. But the accelerating expansion works against this, and for objects that are currently near the cosmological horizon, the light they are emitting right now will never gain enough ground to reach us. The horizon has an effective edge beyond which the future is inaccessible. This means that, over the very long term, the observable universe will change in a way that makes the sky gradually quieter. Galaxies near the edge of the observable universe are already quite close to the cosmological horizon, the limit beyond which their future light will no longer reach us. Over tens of billions of years, more and more galaxies will cross this horizon, their light becoming increasingly redshifted, fading to lower and lower frequencies, dimming toward the infrared, and then the microwave, and then wavelengths so long that no conceivable instrument could detect them. They do not disappear, they continue to exist, presumably in their own part of the universe, their stars burning, and their own local processes ongoing. But the light they emit will no longer be able to reach us. From our perspective, they will gradually become invisible. Not gone. Simply unreachable. Think of it as a slow dimming, spread over timescales so long that no civilization could observe the change in progress. The sky of 100 billion years from now would look different from the sky of tonight, emptier, the distant clusters faded, the deep field images showing fewer and fewer sources as the most remote galaxies cross the horizon one by one. It is a change happening right now, in principle, but on a schedule so slow that it is, for all practical purposes, invisible in any human time frame. Tonight, the sky is full. It will remain full, in any meaningful observational sense, for an extraordinarily long time. The rate of the universe's expansion appears to be increasing. The expansion is not simply coasting at a constant rate from whatever initial impulse gave it momentum. Something referred to as dark energy, for lack of a more specific name, is causing the expansion to accelerate. Dark energy is the dominant component of the universe's total energy budget, making up roughly 68% of the whole. Ordinary matter, the kind that forms stars and planets and gas clouds and everything visible, accounts for only about 5%. Dark matter, which interacts gravitationally but not through light, accounts for roughly 27%. And dark energy, mysterious and uniform and distributed through all of space, accounts for the rest. The nature of dark energy is genuinely unknown. It behaves, in its observed effects, like a property of space itself, a kind of energy inherent to the vacuum, present even where no matter or radiation exists, and remaining constant in density even as space expands. This is different from how matter and radiation behave. Both thin out as space expands, because the same amount of stuff is spread across a larger volume. Dark energy does not thin out. As space grows, the total amount of dark energy apparently grows with it, maintaining the same density throughout the expanding volume. This is why its influence increases over time relative to matter and radiation. As matter dilutes and radiation dilutes, dark energy stays constant, and so it comes to dominate the universe's dynamics increasingly as time goes on. The consequence of this accelerating expansion is that the future universe will become increasingly sparse in terms of what can be observed from any particular location. The galaxies within the local group will remain, bound together by their mutual gravity, immune to the expansion at their scale. But everything outside the local group will, on timescales of tens to hundreds of billions of years, recede beyond detection. The universe of the very far future will be a different place from tonight's universe. Isolated island systems, the remnants of merged galaxy groups separated by ever-growing voids of expanding space, with no light reaching them from outside their own gravitational family, and the stars within those systems slowly aging and dying according to the processes that govern stellar evolution. The local group will persist. The galaxies bound within it, the Milky Way, Andromeda, and their companions, will remain gravitationally connected regardless of the universe's expansion. Eventually, in the very far future, the local group will likely merge into a single large structure, the Milky Way and Andromeda first, the merger playing out over several billion years, the two spiral galaxies losing their separate identities as their stars are redistributed into the broader orbits of a combined elliptical-like structure. Then the other companions of the local group will accumulate over time, drawn in by the gravity of the growing central mass. The resulting system, whatever it looks like after billions of years of merging and settling, will remain as an island in an increasingly empty, observable universe, a gravitationally coherent place, surrounded by expanding darkness, where once the clusters and filaments of the cosmic web were visible. But that is an extraordinarily long time away. The universe is currently about 13.8 billion years old, and the stellar era, the period when stars are forming and shining at significant rates, extends for perhaps another 100 trillion years before the last low-mass stars burn out. 100 trillion years is approximately 7,000 times the current age of the universe. Within that immense span of ongoing stellar life, the universe remains populated and illuminated, and broadly recognizable in its large-scale structure. The expansion that will eventually carry distant galaxies beyond detection is, right now, gentle enough that an enormous fraction of the universe is still visible and will be for a very long time. The cosmic web is still intact. The clusters are still connected by their filaments. The deep field images still show thousands of galaxies in every small patch of sky. There is something stabilizing about placing yourself inside that timeline, even loosely. The universe is not winding down tonight. It is not even particularly old by the standards of its own future. It is in the middle of a long, productive, illuminated phase of its existence. And the light from that phase is arriving in every direction, and the sky is full of it. The expansion is real, and its long-term consequences are real, but they operate on timescales so far beyond the present that they have no bearing on the night. Tonight is simply a night in the middle of the universe's long, productive era, when the sky is full and the light is arriving, and everything is, in the broadest possible sense, ongoing. The light of distant galaxies that is visible tonight is light from a still active, still producing universe, one that has been building and evolving for nearly 14 billion years and has a very long time still ahead of it. The expansion that will eventually carry those galaxies beyond detection is, right now, gentle enough that a significant fraction of the universe is still visible and will be for a very long time. Tonight, the sky is full. The galaxies are there in every direction, at every depth. And the light is arriving. There is a particular image that settles naturally here of lights on a still and open sea, not going anywhere fast, drifting slowly with the current, each one carrying its own illumination across the water. You cannot see all of them. The farthest are too faint, too stretched, too deep in the infrared to register without special instruments. The most distant are already beyond the reach of anything that will ever be built. But a great many of them are still there, and their light is still on its way, and some portion of it, arriving here, is being received by every instrument and every open eye turned toward the sky tonight. The ones you cannot see are not gone. They are simply quiet at this distance, their signals too faint and too stretched to reach you, but present nonetheless in their own part of the universe, carrying on without any need for witnesses. Nothing about any of this is urgent. Nothing is being lost on any timescale that matters to tonight. The lights are simply where they are, doing what they have always done, sending their signals outward in every direction at the speed of light, which is all they can do and all they need to do. The expansion continues. The light continues. The galaxies turn. And somewhere in the middle of all of that, in a very ordinary part of a very ordinary galaxy, it is night, and the air is still, and something quiet and real is arriving from a very long way away. The universe, expanding steadily in all directions, is not troubled by its own size. There is a thought that becomes available at the end of a drift, like this one, not a conclusion, not a revelation, but something softer than either of those. It is simply this: everything you have heard about tonight is still happening right now and has nothing to do with whether you were listening. The galaxies in the local group are still turning, each star in its orbit, the whole slow gravitational arrangement continuing without pause. Andromeda is still drifting toward the Milky Way at roughly 110 kilometers per second, and nothing about that has changed in the time you have been here listening. The Virgo cluster is still full of its thousands of galaxies, their stars burning, their gas cooling or heating, their central black holes quiet or active, depending on what is near them. The quasars at the deep edge of what is observable are still erupting with their enormous energies, and their light is still departing in all directions, and some of it will reach this part of the universe in billions of years, long after everything that is currently alive has given way to whatever comes next. The cosmic web is still there, still organized into its filaments and knots and wide-open voids, and it continues to slowly shift, the matter flowing along the threads of dark matter that have guided its arrangement since the universe was young. None of this requires observation to continue. The universe was here before anyone could see it, and it will be here long after any particular act of seeing has ended. Light from galaxies you heard about tonight has been traveling toward you for an enormous time, and some of it arrived at your eyes or your instruments without announcement, without ceremony, as a small trickle of photons carrying the image of something that existed long before this world was formed. You were, for a moment, the destination of a very long journey. That is true of everyone who has ever looked up at a clear, dark sky. The light does not know where it is going. It simply goes. And when it arrives, and someone is there to receive it, something quiet and real has occurred. There is nothing demanded of you by any of this. You can hold it loosely, or let it drift away as sleep arrives. The universe does not require your attention in order to continue. It will go on precisely as it always has, patient, enormous, indifferent, in the kindest possible sense of that word, and the light will keep traveling, and the galaxies will keep turning, and the long drift of things will continue in every direction at once, without urgency, without rush, without any particular end in sight. You were here. The light arrived. That is enough. And yet there is still a little more of the night left, and it seems right to stay with it a little longer. Consider the Magellanic Clouds, those two irregular companions to the Milky Way, visible from the southern sky as soft, detached fragments of light. They are there right now, whether or not anyone is looking at them. The large Magellanic Cloud is turning slowly, its star-forming regions still producing new stars from the gas compressed by tidal forces from the Milky Way. Those new stars are igniting tonight, Not tonight in any human sense, but tonight in the sense that at this moment, in the universe's long calendar, that process is ongoing and unpaused and entirely indifferent to the hour. The gas collapses. The temperature rises. The pressure builds. A star begins. It has nothing to do with whether you are awake or asleep. It has nothing to do with whether this planet exists at all. It is simply what cold gas does, under the right conditions, in the presence of gravity, given enough time. The stars that already exist in the Magellanic Clouds are burning through their fuel at rates determined by their mass. The largest ones, the hot, blue, short-lived ones, are already on their way toward the dramatic ends that large stars meet: a collapse, a rebound, an explosion of light and energy that briefly outshines the entire galaxy containing them. The smaller stars, the quieter ones, are settling into the long, slow, middle phases of their lives, where very little happens very quickly, and the change is so gradual that billions of years can pass without anything obviously new occurring. All of this is happening right now, in both Magellanic Clouds, as you lie here. The Andromeda Galaxy, that faint smear in the northern sky that 2.5 million years of light travel has delivered to us in its current form, is also ongoing. Its 1 trillion stars are each following their own orbital paths around the galaxy's center. Some of those stars have planets. Some of those planets may have conditions that have allowed something to develop on their surfaces, something we would not recognize and could not easily define, or something not unlike what has developed here. We do not know. We may never know. But the orbits continue regardless, the planets circling their stars, the stars circling the galactic center, the whole enormous structure rotating slowly on a timescale of hundreds of millions of years per turn. The Andromeda Galaxy is also, right now, falling gently toward the Milky Way. Both galaxies are moving through their respective orbits within the local group, and their mutual gravitational attraction is drawing them incrementally closer. Every second, they are approximately 110 kilometers nearer to each other than they were the second before. In a single night, the distance between them decreases by perhaps 9.5 million kilometers, a figure that sounds meaningful, but represents a change of essentially nothing against the 2.5 million light-years separating them. The approach is so slow that it is invisible over any timescale a human civilization could observe. And yet it is real, and it is happening, and it will continue happening long after tonight. At the center of the Milky Way, the supermassive black hole sits quietly. It is not accreting much material at the moment. It is not producing the jets and radiation of an active quasar. It is simply present 4 million times the mass of the Sun, contained within a region of space not much larger than the distance between the Sun and Earth, curving the space-time around it into the deep geometry that defines a black hole's presence. The stars nearest to it are orbiting it at speeds that would take them around the entire solar system in a matter of days, their orbits precise and predictable and entirely natural. Nothing dramatic is occurring there tonight. It is just a very massive, very compact thing, doing what massive compact things do, which is mostly to sit and exert gravity. The filaments of the cosmic web, those enormous structures of gas and dark matter stretching across hundreds of millions of light-years, are also unchanged by the night. Matter is flowing along them, very slowly by any standard, drawn by gravity toward the denser nodes where galaxy clusters accumulate. The gas in the voids is cooling in some places and being pushed around in others by the jets from distant active galaxies. The clusters at the intersections of the filaments are slowly growing, adding the occasional infalling galaxy to their populations, heating the intracluster medium a little more with each accretion event. None of this is fast. All of it is continuous. The very distant galaxies, those faint infrared points at the edge of what current instruments can detect, those early compact star-forming systems that existed when the universe was only a few 100 million years old, those galaxies have not been those things for a very long time. The light we receive from them is 13 billion years old. In the time that light was traveling, those galaxies continued to evolve. They formed more stars, or stopped forming stars, or merged with neighbors, or were absorbed by larger structures. What they are now, what they have become in 13 billion years of ongoing change, is not visible to us. It is beyond the light we have received. It is in the universe's present, which is not accessible from here. This is one of the stranger and more restful aspects of the universe, as it is actually structured. The present moment of a galaxy 13 billion light-years away is entirely inaccessible to us. We cannot see it, cannot detect it, cannot know it. It exists, presumably, but it is separated from us, not just by distance, but by the fundamental constraint that information cannot travel faster than light. The galaxy's present is happening, right now, in its own part of the universe, and it will remain unreachable forever. We have only its past. And its past is beautiful, and faint, and reddened by its long journey, and entirely real. There is a kind of permission in all of this. The universe is so much larger and longer than any individual awareness of it, that no single night of listening, no particular act of attention, no one person's wakefulness or sleep makes any difference to its operation. You can listen carefully, or you can drift away before the end, and either way, the galaxies continue. Either way, the light travels. Either way, the slow processes of stellar birth and galactic rotation and cosmic expansion proceed on their own unhurried schedule. Your attention is a gift you give to yourself, not a requirement the universe has placed on you. And so the night settles. The drift has moved from the near shore of the local group all the way out to the edge of the observable universe, through clusters and superclusters and the web of filaments, past quasars burning at the edges of comprehension, past the earliest faint galaxies visible in infrared, and back here again, back to the quiet and the dark, and the simple fact that you are lying somewhere on a small planet, in a modest galaxy, at the edge of a supercluster, in one small section of a universe that extends in every direction farther than light has had time to cross. That is where you are. It has always been where you are. And it is, in its own enormous and indifferent way, a remarkably ordinary place to be. Ordinary in the sense that there are likely many places like it, spread across the universe's vast reach. Ordinary in the sense that the same physics applies here as everywhere else, the same constants, the same rules, the same slow operation of gravity and light and time. And yet here you are, receiving the light, existing in the moment, part of a universe that did not arrange itself around you, but that includes you anyway, the way a long river includes every particular drop of water that moves through it. The light will keep traveling. The galaxies will keep turning. The expansion of space will continue in every direction at once, gently, without drama, at the pace the universe has always preferred. You were here. The light arrived. That is enough. Sleep well, and good night.